Let's talk about a real sorting algorithms. Okay, insertion sort. So insertion sort is similar to the previous sorting algorithms, but it is more efficient sometimes. Okay, so basically pick one record from unsorted list and insert it into the sorted list. Okay, so here is an example. So this is an input list. Okay, and we start from the second element, 25. And we compare this one to this one. So since 25 is larger than 4, then it stays there. Okay, that's it. And next, we check this 9, and from we want to put this 9 in the middle of this list. So basically we have two sections. Okay, so the light blue colored list or the white colored list. Okay, so white blue colored list is in a sense it is sorted. Okay, and white colored list is kind of untouched element. Okay, so 4 and 25 is kind of sorted sublist, and then we want to put this 9 in the middle of this. Okay, so 9 is smaller than 25 and larger than 4, so we put 9 in the middle of these two, between these two. And in the next step, we want to put this 37. Okay, and then 37 is larger than 25, so we keep it as it is. Okay, now next 2. And 2 is smaller than 37, and then 25, and 9, and 4. So 2 goes here. Okay, then this is our sorted list. Okay, so the idea is simple. So first, we start from the second element because we can assume that the first element is sorted already. Okay, no matter what it is sorted. And then we let's say if it is like 4, 2, 9, 37, and 25. Okay, if this is the original list, then when we start with the 2, then actually it will be 2, 4, 9, 37, 25, right? Because 2 is smaller than 4. But in this case, 25 is larger than 4, so this is the sorted list. And now we put 9 between these two because 9 is right. So every time we put one element in somewhere in this sublist, okay, every time. So we put this 37 somewhere in this sublist, okay, and then it will be sorted. So likewise, every time we pick one element from unsorted list and we put it in the sorted list. So that's it. Okay, so let's implement the algorithms. Okay, so we get the list array and the total number of element. Okay, now we have one for loop. It goes from 1 to n-1. See, in the previous slide, we said, we assume that the first element is already sorted. So we start from the second element to n-1. Okay, and then list I will be copied to the next. Okay, so we just copy that. So I mean, in this list, let's say these are already sorted, and then this is our I, and we copy this element to the next. Okay, now j goes from i-1. So since this one is I, j goes from here. Okay, and then as long as j is positive or is 0, and as long as next key is smaller than the list j key, okay, then j goes down. Okay, so basically we compare this one and this one. If this one's key is smaller than this one, then j goes down. Okay, and whenever we decrease j, then we copy list j to list j plus 1. So this one is, let's say this one is j, and this one is j plus 1. in this case j start from I minus 1, so this one is j. Okay, sorry, so this one is j, and this key is, if this key is smaller than this key, then this one will be copied to this one. Okay, basically we are shifting all the larger elements to the right side, so we copy this one, and if this one is larger than this one, then we stop, and then we copy these elements to these positions. Okay, so this is it. So if you understand the algorithm, then we can understand this implementation more easily. Okay, so it looks like this is similar to selection sort algorithms, right? But there is a benefit here. So in the worst case, we need n square in the computational cost, because we have to check all the elements, and then with one specific element, then we have to check all the elements to find out the perfect locations. Okay, so in the worst case, it takes n log n, n square. But in the best case means, okay, this is already sorted. So this original list is already sorted. Okay, then what happens? Okay, when we check this one, oh, this one is larger than this one, then we don't swap. Okay, so when we check this one is larger than this one, we don't swap, we don't shift. When we check this one is larger than this one, okay, we don't touch. When we check this one, so just one comparison for one element is enough. So we take just n, in a bigger notation, n is enough. Okay, so for the best case, we need n in a bigger notation. But in the selection sort algorithms, we need n square. Even with the best case, even the original list is sorted, then it took like n square, right? So this is kind of the one benefit of insertion sort. Okay, then we can make a little more variations. Okay, think about this algorithm. So we start from the second element, okay, and then we put this one into this sublist, sorted sublist. So let's say we are checking this element, then basically the algorithm says, okay, we have to put this element somewhere in this sublist. Okay, so we have to find out the best place. Okay, so it's like insertions. So this is a sorted list, and we are inserting new element. Okay, so if we understand this problem as insertion, so then we can use binary insertion. We can use binary search to find out the perfect locations. So that's binary insertion sort. So to find out the best place, perfect place, then if we use a binary search, then we need the log n, right? So instead of n squared, then it could be n log n if we use binary insertion sort. Okay, and then we can take one step further. So instead of using an array, okay, then what if we use a linked list? Then it is a linked insertion sort. So if we use a linked list, then look at this one. If we use an array, then every time we have to shift some elements like this. And to shift one element to the next, then we have to do this in the memory space, which is computationally huge. It's really expensive. But if we use a linked list, then we have to find out the perfect location, and then we can just insert a new element in that position. And we don't have to shift anything in the memory space. We just change some pointers. That's it. So this is better. Okay. Now we have a quick sort. So as the title says, this is quick. So in general, a quick sort algorithm is the fastest. Okay. Okay, so let me explain the algorithm first. Okay, we have lots of stages here. Okay, and at each stage, pick a pivot element and partition list into two sublists. Okay, and then the left side will be a set of smaller elements, and on the right side we have larger elements. Okay, and then we will do that. We will do the same thing to each sublist. Okay, so let me explain this. So given this list, and pick a pivot element. So without loss of generality, let's pick just first element. Okay, so just pick the first element as a pivot number. Okay, and then we will move all the elements that are smaller than p0 to the left side. Okay, maybe these ones, who knows, and some other elements who are larger than the pivot will go into the right side. Okay, so basically we have two partitions with one pivot. Okay, so by partitioning we are kind of somehow this is more kind of sorted than this. Okay, so based on this we have smaller elements and larger elements, so it's kind of sorted but not exactly. But these ones are smaller than this one and smaller than this one, right? Perfect. So we can do the same thing to each partition. So this one is not sorted and this one is not sorted, so we apply the same thing to this and to this. So we apply the same thing twice. So after partitioning like this, then let's focus on the left list and the right list. On the left list, we do the same thing. So we pick the first element as a pivot number and arrange the other elements. So that we have all the small elements on the left side and all the large elements on the right side. Okay. So likewise, pick a pivot number with the first element. Okay, and then arrange all the other elements, so that the smaller elements will be on the left side of this pivot and the large elements on the right side of this pivot. Okay, then we have a little more sorted than before. And then if this one is more than one element, so if we have two elements or more than two, okay, so as long as it is not one element, then we apply the same thing. If this is just one element, then this is sorted, so we cannot do any more. So we can keep doing this until we have one element in these partitions. Otherwise we apply. So sometimes, let's say, we have one element in the left side, but we have 5 elements on the right side. Then we don't apply the same thing to this partition anymore, because we have only one element here, but we have to apply this thing a couple of times, because this is longer, way much longer than this. Okay, but still the idea is quite simple, right? So as long if we apply the same thing until we get just one element, then we will get a sorted list as a result. So let me explain this quick sort with this example. Okay, so with this example, then I can explain the algorithm in detail. Okay, so this is our original list. This is not sorted. Okay, and then pick the first record in the list as a pivot. So 26 is pivot. So why the first element? Because it doesn't matter, because this one is unsorted. It doesn't matter. If you want, you can pick 19, but there is no difference because this is unsorted. If you want, you can pick the second element or third element, but without any loss of generality. So let's pick the first element. Okay, there is no difference, so make it simple. So first element. So now from this Okay, so we have two indexes. First one goes from here to the right side, and another index goes from here to the left side. Okay, so while we are moving, whenever we meet an element which is larger than 26, okay, so while we are moving on these directions, whenever we meet any key who is larger than 26, then we stop. Okay, and then from this index, whenever we meet a key which is smaller than 26, then we stop. Okay, so in this case, 5 is smaller than 26. Okay, we pass, and 37 is larger than 26, so we stop. Okay, and from here, 19 is smaller than 26, we stop. Okay, good. So we swap. Do you see that? By swapping, it is kind of sorting. Okay, so 19, smaller one, will be on the left side, and 37 will go to the right side. Okay, so now we have this list, and then we keep doing this. Okay, from here, okay, let's check next one. 1 is smaller than 26. Okay, perfect, pass. And 61, which is larger, and stop. And 48, which is larger, and pass. And 15, smaller than 26, stop. So 61, 15, we swap these two elements. Okay, then now we check 11, which is smaller than 26. Okay, 59, larger than 26. And then now we pass, right? So this index is larger than this index, then we don't do anything. Okay, so this one is the kind of the last element in these directions, and 59 is the last element in these directions. Okay, and then we swap these two elements, 26 and 11. So 11 is smaller than 26, so it doesn't matter where it is as long as it is on the left side. Okay, so 11 goes to here, and 26 is here. So now 26 is actually a pivot number. So on the left side of 26, we have a small elements. On the right side of 26, we have large elements. Okay, so this is one stage, one pass. So now we have kind of sorted. Okay, we have sorted. And then, as I said, we can apply the same thing to this list. Okay, and we apply the same thing to this list. And if we keep doing this, then finally, eventually, we are going to get a sorted list. That's it. Okay, so let's implement these algorithms. Okay, so we have basically we are going to use recursive solutions here. So we have a list and left index and right index. So originally, if we have 5 elements, left will be 0 and right will be 4. Okay, so when we call this function from main functions, then we pass this list, and then we pass 0 and 4 to indicate the boundary of this list. Okay, and then as long as left is smaller than right, then we will do this. Okay, otherwise we don't do anything. Okay, and then I goes from left, so here is I, and J goes from right plus 1, so J is pointing this one. Don't worry. Okay, so J goes from right 1, and then pivot is the first element. Left is actually the first element, so pivot is the first element of this list. Okay, and then this part is critical. So in this do while loop, we have another do while loop here. So we actually increase I first. So now I is here, and then we check. Okay, we check if I is smaller than right, and and the list I key is smaller than pivot. Okay, so if this key is larger than or equal to pivot, then we stop there. Okay, let's say this one is larger than pivot, then we stop. The variable I stops here. And j, we decrease j first. So j is here without anything. J decrease. So j start from here. As long as j is larger than left is index. And as long as list j key is larger than pivot. Okay, and then as long as these conditions are satisfied, then j goes down. Okay, and then if we made a smaller element than pivot, then j stops here. And then we check if r is smaller than j, then we swap these two elements. Okay, and then as long as I is smaller than j still, then we keep doing this. So we go back to this loop again and again and again. And then after finishing this do while loop, then we swap. This means we actually swap the first element. The first element was a pivot. So we swap this first element with the j. J is the last element of the smaller one. Okay. So now we finish one kind of partitioning. So given this list, we actually, by this statement, we actually put the pivot number, and then we have small elements and the larger elements. Okay, good. And then we call this quick sort function with these boundaries. So when we call quick sort first, we pass left and j minus 1. So basically when we call this function, we will focus on this sublist. And when we call these functions, then the boundary says j plus 1 and the right. So basically, we are going to focus on this list. Okay, this is the implementation of quicksort algorithm.